Welcome to the lecture series of Information and Network Security. So in our previous class, we had started with the introduction to cryptography, and then we happened to see the basic terminologies of crypto, which included cryptology, cryptography, cryptanalysis, and crypto altogether in it. Right? So after it, we happen to explore more about what is a cipher, right? So cipher is basically the encryption of the plain text, right? And the result that is generated is known as ciphertext, right? And when we decrypt a ciphertext, we convert it back to a plain text, and a key is used to configure the crypto systems. So there are two different types of crypto systems. One was known as symmetric crypto systems, symmetric key crypto systems, and the other one was known as public key crypto systems, right? So in case of symmetric key crypto systems, we used same keys to encrypt as well as to decrypt. But whereas in case of public key crypto systems, we used public key to encrypt, right? Public key to encrypt, but whereas private key to decrypt, right? So then we happen to see the diagram, right? And we go with an assumption that the attacker is well versed with the system. He knows all the algorithms. Only thing that is secret is the key, right? So crypt algorithms are no longer secret. So this assumption is known as Kirchhoff's principle, right? So having known all these things, we then happen to see the block diagram, right? That is the generic view of symmetric key crypto, right? So when we say symmetric key crypto, we saw that the key used for encryption as well as the key used for decryption were the same one. So encryption is converting this plain text into a non-readable format known as ciphertext using the key here, right? And then this ciphertext would be converted back into a plain text, that is into a human readable format, by making use of a key, so which is known as decryption, right? So in case if this key used for encryption was a public key, right, and the key used for decryption was a private key, then we call it to be the public key crypto system, right? So then, so today we are going to look into some of the ciphers, classic ciphers, right? So if we are going to examine 4 different classic ciphers here. The very first one would be the simple substitution, right? So it is one of the very oldest cipher system that is used, right? And then we have double transposition ciphers. Then we shall be exploring the classic code books, followed by one time pad, right? So let us begin our discussion with a simple substitution cipher, right? Okay, so first we consider a particularly simple implementation of a simple substitution cipher. So in the simplest case, the message is encrypted by substituting the letter of an alphabet n places ahead of the current letter. So for example, we are given with a plain text. We are given with a plain text which is 7 years ago, right? And let us say the key that we have considered is the value n, and let us consider the value of n is 3, which means that you're trying to substitute the letter of the given alphabet in the plain text by an alphabet that is n places ahead of the current letter, right? So the substitution which acts as a key is N, right? So here, now consider a plain text. So you can see a table here. So the plain text has alphabets ranging from small a to z, right? So their equivalent ciphertext will be an alphabet in capital letters that is placed after n places of the current letter. So if I consider the current letter as A, then I find D to be placed after 3 places ahead of A, right? So the capital D now becomes a cipher which represents a plain text small letter A. So similarly, if you again observe here, let us observe the alphabet B. So 3 places ahead we have 1, 2, 3. So 3 places ahead we have E there, right? So capital E here now becomes the ciphertext of the alphabet B, right? So then we in this particular example we have followed the convention that the plain text is in lowercase and the ciphertext is in uppercase, right? And we are using key as 3. So now we can encrypt the plain message four score and 7 years ago by looking up each plain text letter in the table and then substitute its corresponding letter from the ciphertext row, right? Or by simply replacing each letter by the letter that is 3 positions ahead in its place in the alphabet, right? So therefore if you observe here, F is now yes F is now converted into I. So this is a ciphertext that has been generated for the message 4 score and 7 years ago. So similarly O here shall be replaced by cipher R, right? And then U here would be replaced by the cipher X, right? And so on. You are going to replace every plain text in this message with its equivalent ciphertext to generate the ciphertext message to be something like IRXU, VF, RU, HDQG, and so on, right? So to decrypt this simple substitution, that is decryption in the sense converting back this ciphertext into a plain text, what we can do is we can simply look up the ciphertext letters, right? We can simply look up the ciphertext letters in the ciphertext rows and replace them with their corresponding letter in the plain text row, right? Or we can shift each ciphertext letter 3 letter backward by 3. So I'm sticking on to 3 because with respect to this example we had considered key is equal to 3, right? So the simple substitution with a shift of 3, if the shift always remains 3, then it is also known as a Caesar cipher, right? I repeat, the simple substitution mechanism with a shift of 3 is known as cipher Caesar, right? So then if we limit the simple substitution to shifts of the alphabet, then the possible keys would range, or the possible keys, that is the value of n, would belong to a set which has elements 0 to 25 in it, right? So n would be ranging from 0 to 25 as we have 26 alphabets in English language, right? So I mean to say that if we are trying to limit the simple substitution to shifts of the alphabet, then the possible keys would be 26 there, right? So now the intruder, right? So the intruder can intercept the ciphertext message, and she can suspect that it was encrypted with a simple substitution cipher using a shift by n, right? So what she can do is he or she can try each of the 26 possible keys for decrypting the message with each uh, putative key, right? And checking whether the resulting putative plain text really makes a sense, right? So if the message really was encrypted via a shift by n, then the intruder can expect to find the true plain text, right? And therefore this mechanism of trying to find out the true plain text is now known as brute force attack, right? Brute force attack, in the sense the intruder simply goes on trying for various values of n as the key, and at some point in time he shall find the value of n such that the plain text message uh, really makes a sense when it is read, right? So this type of attack we call it as a brute force attack, and this he can he can attempt for a brute force attack if he has enough time and resources, right? Because he will be eventually stumbling across the correct key and breaking the message there, right? So this is the most elementary of all crypto attacks, right? And it is known as an exhaustive key search. Okay, so then we move on to the next next type of ciphers here, right? So suppose, yeah, suppose how do we decrypt a message using a Caesar cipher? Suppose we know that the Caesar cipher is being used, that is, you have made a shift by 3 alphabets, right, ahead in the series, right? So then it becomes very easy to decrypt the given cipher. So for example, if the given cipher is VSRQ, right, and so on, then finding for V in the ciphertext, how we can get back to the plain text messages, finding to the ciphertext V, you can replace it with the plain text small s, and yes, capital S will be converted to small p, capital R will be converted into small o, right? And capital Q will be converted into small n, and capital J will be converted into small g, and capital H will be converted into small e, and so on. If you go, you get back the plain text, right? So I mean to say that decryption in case of Caesar cipher is very easy, as we know that the key value is fixed to 3, right? So therefore you can see the plain text of the ciphertext here. So given is the ciphertext with the alphabets VSRQJ, which is in some scribbled format, right? Doesn't make a sense, but when converted back into the plain text, it means sponge Bob square pants, right? it has a meaning to it. Okay, so then moving on to the next one, that is not so simple substitution, right? So how exactly does this not so simple substitution cipher work? Okay, so here we are shifting by n for some n whose value is between 0 to 25. So as I had already told you that there are 26 alphabets in English language, so therefore n can have a value between 0 to 25. Then this n is considered to be the key, right? And let us consider 7 to be the value of the key n. Okay, so then this table gives us a mapping of plain text to its corresponding ciphertext. So as the key is 7 here, we are considering the plain text to be small letters and ciphertext are there, is given with the uppercase letters here. So A, 7 locations ahead A is B is 1, 2, 3, 4, 5, 6, 7. Right, at the 7th place we have H, so capital H is a ciphertext equivalent for the alphabet, the plain text A. Right, so similarly the ciphertext equivalent for alphabet B will be a letter that is placed 7 uh, that is placed 7 letters ahead of the alphabet. So capital I here now becomes the ciphertext for the plain text B, and so on, right? So then cryptanalysis, yeah, try them all. A simple substitution, shift by n is used, but the key is not known. Okay, so given is the ciphertext, how do you find the key? So in this case, as we have only 26 alphabets in English language, it means that the key value can range somewhere between 0 to 25. So what you are going to do is you are going to try decrypting this message for all the values of keys, that is starting from n is equal to 0 to 1 and so on till 25. Changing the value of n, you are going to try decrypting the given ciphertext. So we called it to be the exhaustive key search. So it requires a lot of time, right? So if the intruder starts with the very first value of key as 1, then for this given ciphertext he will find a solution when n is equal to 4, right? So then simple substitution, right? So in general, simple substitution key can be any permutation of letters, right? And not necessarily a shift of alphabet. Okay, so let us say A is given as J, right? And B is given as I. So it any a plain text can take uh, any other alphabet as its ciphertext equivalent, right? So it means that a given alphabet will have 26 possibilities of occupying the place in this ciphertext row, right? So J as of now is placed in the first column here. So if I want to place J somewhere else, then I still have 25 locations among which I can choose one, right? So it means that one alphabet has 26 places wherein it can sit in the ciphertext column. So similarly, all 26 alphabets of English language are now having 26 possible permutations. So permutation is nothing but we're talking about the arrangement there. So therefore the possible number of keys will now become 26 factorial, right? So 26 letters can take 26 different places in forming ciphertext. Then you have 2 raised to 88 possible keys, right? So it is like you're trying to increase the number of keys, and when the number of keys are going to increase, then decryption will become very difficult, right? So then we know that the simple substitution is used, but we really don't know whether you are making a shift by n, then finding the key for the given cipher really becomes difficult, because we cannot try all 2 raised to 88 simple substitution keys, right? So we need to be more cleverer here, right? So it is totally depending upon the English letter frequency counts. Okay, so then let us move on to some more terminologies here. So crypto system is said to be secure if it best know the attack is to try all the keys, that is the exhaustive key search, right? And crypto system is insecure if any shortcut attack is known, right? But then insecure cipher might be harder to break than the secure cipher. Okay, so now we move on to the other mechanism, that is double transposition. So how exactly is double transposition going to work? So okay, to encrypt or a double transposition cipher, what we do is we first write the plain text into an array of a given size, right? So let us say we are given with a plain text attack x at, okay, so x is okay, let us say it. So attack x at x done, right? So the plain text is given. Okay, so now we first write the plain text into an array of a given size. So let us say we are given with an array of 5 rows and 3 columns in it. So if you can see, we start with ATT, then ACK, and followed by XAT, right? XAT, XDA, WN, right? So the same plain text is now being arranged into a 5 by 3 matrix, right? And then we try to permit the rows and the columns according to the specified permutation here. Okay, so we are going to permit the rows and columns. So when I say permitting the rows and columns, for example, if I can make use of any permutation. For example, if I have the rows 1, 2, 3, I can rearrange them in the form 3, 2, 1, right? And then once I permit the rows, then I go on to transposing the columns, right? So if I have columns 1, 2, 3, and 4, I can transpose it in terms of 4, 2, 3, and 1, right? So here the row permutation. So in here you can observe the row 1 has a TT in it. So here it is come to row, it has become third row. So permutation here is rows 1, 2, 3, 4, 5 have now been rearranged in terms of row 3, 5, 1, 4, and 2. You can follow any permutation. So the manner in which you are going to permute the rows and columns is not fixed here. So you can follow any permutation pattern here, right? So the first row, first, second, third, fourth, fifth row in the permuted matrix is now arranged in terms of row 3 appearing to be the first one, row 5 in the second place, row 1 in the third place, row 4 in the fourth place, and row 2 in the fifth place here, right? And then the column transposition is performed. So columns were initially in the order 1, column 2 and column 3. So in the resultant matrix they have been transposed to appear in the order column 1, column 3 and column 2, right? So let us consider the first row here. So first row has alphabets A, T, T in it. So it is now come to the third place in the double transposition matrix, right? So ATT itself here, and then first column's value will remain at its own place. So A will remain in the first column, right? The second column has the alphabet T in it. So second column now moves on to the third place. So T is placed here, and similarly the third column also has a T in it. So third column now appears to be the second one here. So again we have a same alphabet T. So here you cannot make out a difference. So let us look into row number 4 here. Okay, so look into row number 4. So row 4 in the resulting ciphertext is also at its same location, right? But now column 1 has an X here. So column 1, as the permutation of columns say that column 1 will remain at its own place, so X shall be placed here. But then column 2 in the actual matrix will now be a part of third column in the transposition. So D is placed here, and then A, the third column's value, is placed in the second column here. So if you see, the alphabets have been interchanged, right? So we have performed the transposition there, right? So to encrypt with double transposition cipher, what we do is we first write the plain text into an array of a given size and then permute the rows and the columns according to the specified permutation. So you can consider the permutation to be of any form here, right? Okay, so now let us consider that the ciphertext that is given is XTAWXN ATTXA, right? So whatever we obtain from this matrix is known as the ciphertext. So it is XTAWXN, right? And ATTXADAK, C, right? So this is the ciphertext. Okay, so the key here, right, for double transposition, the key consists of the size of the matrix and the row and the column permutation. So if anyone knows the key, can simply put the ciphertext into their appropriate sized matrix and undo the permutations to recover the plain text, right? Okay, so we shall stop here for now. We have seen double transpositions also. So in the next lecture we shall look into one time pad.